Hi, in this chapter I'm going to talk about the gases. All right, what's a gas? Gases, they uniformly fill any container and therefore they assume the volume of the container and that's why we say gases have no definite volume. Also, they mix completely with any other gases and they exert pressure on their surrounding, or if they are in any container, they exert pressure on the walls of the container. One more characteristic of gases is that they have no definite shape. They have no definite shape. Which means they take the shape of its container. And these are some of the important characteristics of gases. Now let's talk about kinetic molecular theory. This theory was discovered, and it talks about the behavior of gases. It kind of helps us to understand the behavior of gases. This model predicts how gases behave under different conditions. And just like any other models, kinetic molecular theory, it's not perfect and it does not work under some conditions. Now, let's talk about the kinetic molecular theory. Okay. The first thing that it says is that gases or gas particles, they move in a constant straight line motion. That's one of the behavior of gases. Also, they do not attract or repel each other because they are so apart. There is a huge space between the gas particles compared to the size of their particles. That's why they do not interact, they do not attract or repel each other because they are so far away from each other. And one other behavior is that gas particles, their motion is proportional to the temperature. And that temperature unit that we talk about is in Kelvin, which means if you increase the temperature, the gas particles move faster and faster, and therefore the energy increases. Or which means is that the energy of gas particles is directly proportional. Let me write it this way. Is directly proportional to temperature. Okay? And that's the Kelvin temperature that we are talking about, not Celsius. Okay? That means if we increase the temperature, the gas particles start moving fast and fast and fast, and the energy increases. Okay? Then these four were some of the characteristics of gas particles, which was explained by kinetic molecular theory. Now, based based on what we talked about, these are the conclusion that is made based on kinetic molecular theory of gases. One is gases are compressible, and again that's due to the fact that they do not interact, or they are so apart from each other. Maybe it's better to say because they are, because of large space, let's say because of large space, due to large space between gas particles. They also take the shape and the volume of the container they are in. That's why gas particles have no definite shape and volume. And their density, they have a lower density in comparison to liquid and solid. And why is that? The density is the ratio of the mass over volume. Okay? Then because gas particles are so apart from each other, the volume is large. Okay? That's why for the same mass of liquid and solid, their density is the lowest. Okay? Again, why the density of the gases are the lowest in comparison to liquid and solid? If you think about it, gas particles, there is a large space between them in comparison to the size of them. Then for the same mass of solid, liquid, and gases, their density is the lowest because their volume is the largest. That's why the density of gases is the lowest in comparison to the molecules, in comparison to liquid and solid. Now let's talk about compressibility of gases versus liquid. The gases are easily compressible. Why? That's because they have large space, or they have a large empty space between the gas particles. And that large empty space between the gas particles, as you could see in this picture, make them easily compressible. Okay, that's all got to do with some intermolecular forces. Since they are so apart from each other, their intermolecular forces, which are those forces that hold the gas molecules together, it's so weak. Okay, that's why it's so easy to compress the gases. It's just the space between them, it's so huge. Whereas for liquids, for liquids, they are incompressible in comparison to gases because there is so little space between liquid particles. Then if you compare the spacing between liquid particles and the gas particles, you will see that liquids in comparison to the gases have very little space between the particles. That's why they're a lot more difficult, or they are not compressible in comparison to the gas molecules. Gas molecules are so easily compressible because of the large distance between them, whereas liquids are not compressible because they have so little space between the gas molecules. The next topic that I'm going to talk about is pressure. Okay, let's talk about pressure. What do we mean by pressure? What causes pressure? Then when gas particles, okay, because they are so apart from each other, they could easily move around. Once they could easily move around, what happens is that they hit the walls of the container that they are inside. Okay, and that constant collision between the gas particles and their surrounding, which could be the container they are in, causes pressure. Okay, and pressure is everywhere that we are. It's inside our bodies, inside the veins in our body that blood flows. There is also pressure. Then what causes pressure? It's that constant interaction or collision between the gas particles and the surface they are around or they are in. That surface could be the veins in our body, it could be a container, it could be anything. Okay, that constant collision causes pressure. This is basically how pressure is defined or calculated. In order to calculate the pressure, we divide the force by the area. That's how pressure is calculated. Now, then force, if we are talking about the SI unit and we want to find out the SI unit for pressure, we know that the SI from previous chapters, the SI unit for pressure is, the SI unit for force is Newton. Okay. Also, the SI unit for area is meter squared. That's why the unit for pressure is Newton per meter squared. And this is the SI unit for pressure. And that's how we also calculate pressure, by dividing the force by area. Okay. Now, let's talk about the pressure. The amount of pressure exerted by gas particles depend on so many factors, and one of them is the number of gas particles. Okay, and the number of gas particles, the amount of pressure, it depends on the number of gas particles. And what do I mean by that? Then if you look at this picture, and if you look at these two jars, as you could see, look at the number of gas particles is in the top jar in comparison to the bottom jar. As you could see in the top jar, the number of gas particles is a lot more than it's at the bottom jar. Okay, that is why when you in the same container, if the size of the container is the same, when we have higher number of gas particles, what happens is that there is a higher probability of gas particles hitting themselves and hitting the walls of the container. Okay? Whereas in the bottom jar, when there is a fewer number of gas particles, there is a lower probability of themselves hitting each other and hitting the walls of the container. That's why when the amount of or the number of gas particles is higher, okay, it causes higher pressure. Whereas when we have a fewer number of gas particles, the pressure is lower. Okay, it's like you are in the room that compare if there is 100 people in that room or there is 5 people in that room. Okay, when there are 100 people in that room, there's a higher probability of people bumping into each other. Whereas there's only 5, there's a very low probability of those 5 people bumping into each other. It's kind of the same concept for gas particles. Then for a given volume, when we have a higher number of gas particles, there's a higher probability of them bumping into each other and exerting pressure on the walls. That's why the pressure is higher in comparison to when we have a fewer number of gas particles. As I told you in the previous slide, this is the SI unit for pressure, which is Newton per meter squared, which is equal to 1 Pascal. These are other units for pressure, and these are some more. Then you don't need to memorize the units for pressure, but you have to be able to convert from one to the other. But these conversion values will be all given to you. All you need to know from here is that atmosphere, Pascal, millimeter mercury, PSI, inch mercury, these are all units for pressure. Okay, but you don't need to know the values, conversion values at all. It will be given to you whenever you need them. Now let's do this problem. Okay, what we're gonna do here in this specific problem, we're gonna convert 0.311 atmosphere to millimeter mercury. Then if I go back to the previous slide, this is the conversion value from atmosphere to millimeter mercury. Okay, then 0.311. I'm going to set up my equation so that I could easily cancel out atmosphere, and I will end up with millimeter mercury. Okay, and as you could see, the atmosphere will be easily canceled out. Then I'm going to multiply 0.311 by 760, and I get 236.36 millimeter mercury. Next, we have to take care of the sig fig. This number is 3 sig fig. Then for sig fig, we do not look at the conversion values, and since the given number is 3 sig fig, the answer has to be 3 sig fig. Okay, that's where the vertical dotted line gonna go, and you're gonna write down the rounded number, which will be 236 millimeter mercury. Therefore, 0.311 atmosphere is equal to 236 millimeter mercury. Now the next topic that we're going to talk about is it's gas laws. The first one is Boyle's law. Boyle's law was discovered by Robert Boyle. He's the one that discovered the Boyle's law, and it talks about, and Boyle's law, it looks at the relationship between volume and pressure. That's what it studies. Boyle's law, it's the relationship between volume and pressure of a gas. Okay, as you can see here, the volume of a gas and its pressure, they are inversely proportional. That means as we increase the volume, the pressure decreases. Okay, then if we increase the volume, the pressure decreases, and vice versa. Okay, that sign here means proportionality. Okay, then based on this equation here, the volume of a gas is indirectly proportional to pressure, and this is the equation that defines Boyle's law. But when we are considering all these laws, we always vary two things. Okay, then there are other than volume and pressure, we have temperature, and we have gas particles, or the number of gas particles that they interfere. Okay, then we have pressure, volume, temperature, and the number of moles of gas particles. Okay, then these all affect the behavior of gas particles. Then Boyle's law, what he did was that he kept these two constant. Okay, he kept these two constant and look at the behavior of pressure and volume. And what he discovered was that the volume of a gas is inversely proportional to pressure. That means once he increased the volume of the gas, he saw that the pressure decreased. And this diagram or the graph shows you exactly what happens. And as you could see, as the volume of the gas increases, you go from 20 to 40 to 45, 50. As you could see, the pressure goes down. Okay, and the volume of the gas is inversely proportional to pressure. You increase the volume, the pressure goes down. The next law is Charles' law. It was discovered by, let's use this color, okay, by J.A. Charles, okay. And what he studied the relationship between volume of a gas and its temperature. That's what he studied, the volume of the gas and temperature. Again, these are the variables that affect the gas constant. Then what he kept constant was the number of moles of gas particles and the pressure. Okay, these two were kept constant. Okay, and he studied the behavior of gases when he varied temperature and volume. Then what he did was that he either increased and decreased temperature, and he looked at what happened to the volume of the gases. And what he discovered was that the volume of the gas is directly proportional to temperature. And again, that temperature is Kelvin. Okay, the volume of the gas is directly proportional to temperature, which means if we increase the temperature, the volume also increases, and vice versa. If you decrease the temperature, volume decreases. And this is the equation that defines Charles' law, which the volume of the gas is directly proportional to the temperature. And as you could see in these two graphs, you can easily see as the temperature of the gas has increased, the volume also increased. And again, as the temperature, Kelvin temperature increased, the volume of the gas also increased. No matter what kind of a gas it is, but as it applies to all gas molecules, as the temperature increases, the volume also increases. Okay, and let me ask you a question. What is this number? Okay, we've talked about this number in the past. That number is the absolute zero temperature. This is 0 Kelvin. Remember, that's when everything and anything freezes. We talked about it in chapter 2. When T temperature is equal to 0 Kelvin. Okay? Now, then we talked about Boyle's law. We talked about Charles' law. The next law that we're going to talk about is the combined gas law. That's the combination of Charles' law and Boyle's law. Okay? Then under combined gas law, only the number of gas particles was kept constant. Okay? Whereas the pressure, temperature, and volume was not kept constant. Okay? This is the combination of Boyle's law and Charles' law. Okay? So if you recall Boyle's law and Charles' law, for Boyle's law, the volume of the gas is indirectly proportional to temperature. Then this part of it, which is a different color, okay, then this part of it, oops, this part of it is Boyle's law. Okay, and Charles' law, the volume of the gas is directly proportional to temperature. Okay, then this part is the Charles' law. Okay. Then as you could see, combined gas law is the combination of Boyle's law and Charles' law. But you have to assume that the number of gas particle stays constant. Okay. The next law that we will be talking about is Avogadro's law. In Avogadro's law, we looked at what he looked at was the volume and the number of moles of gas particles. Okay. And then let's choose a different color. Then in Avogadro's law, the pressure and the temperature was kept constant, and he investigated the behavior of volume and the number of moles of gas, and he concluded that the volume of the gas is directly proportional to the number of moles of gas particles. That means if we increase the volume, therefore the number of moles of gas particle also increases. Okay. Also, if you remember, the person that stated this relationship, which was the same person that discovered the Avogadro number. Remember this number? Okay. Particles per mole. It's the same person. Okay. That same person that talked about the Avogadro's number also stated the Avogadro's law. All right. The next law that we're going to talk about is the ideal gas law. Ideal gas law is the combination of Boyle's law, Charles' law, and Avogadro's law. Okay. Then based on Boyle's law, the volume of the gas is indirectly proportional to pressure. Based on Charles' law, the volume of the gas was directly proportional to temperature. And based on Avogadro's law, the volume of the gas was also directly proportional to the number of moles. Then when you combine these three laws, you will see that the volume of the gas is proportional to the number of moles of the gas multiplied by Kelvin temperature divided by pressure. Okay, and that proportionality, which later we give a number to that proportionality value, which is R. Okay, that R defines the proportionality, and it's called ideal gas law constant. Okay, that R, which defines the proportionality, later was given a that let's call it as gas law constant. Gas law constant. Gas law constant. Okay. Right. Now, let's talk about the gas law constant. Then let me go back to my previous slide. Then if I rearrange the gas law constant, I'm going to write it like PV is equal to nRT. It could be also rewritten like this. Okay. Here it's written in terms of V, but I rearranged everything and I wrote it this way. It's exactly the same thing. Okay. This is the ideal gas law equation. Now let's talk about all these parameters or variables in gas law. All right, let's talk about the first one, right, which is pressure, okay, and the unit for pressure has to be atmosphere. What is the second one? The second one is volume, and the unit for volume has to be liter. Okay, N stands for number of moles of gas particles, and its unit is in mole. Okay, let's talk about T. Is temperature, and its unit has to be in Kelvin. And R, as you could see here, is the ideal gas law constant, and this is its value. Okay, as you could see, the unit for gas law or ideal gas constant is liter times atmosphere per mole Kelvin, and that's because of that when you are doing any calculation involving ideal gas law and ideal gas law equation, you have to make sure that your unit for your pressure is in atmosphere, the volume is in liter, the number of moles is in mole, and temperature is in Kelvin. If not, you have to convert it. If you don't convert it and you plug in the numbers, it's not going to be correct, because the unit for pressure, volume, number of moles, and temperature, the unit for them has to match the unit for ideal gas constant. This number, it will always be given to you. You don't need to memorize it at all. Okay, this is the rounded number. We have also an unrounded number for ideal gas constant, which is equal to 0.08206 liter atmosphere. And whenever you are doing the calculation, use this unrounded number. Okay, and as I said, I will always give that number to you. You don't need to memorize it. Now, let's do this problem. Okay. According to this problem, what we want to find out, we want to calculate the volume of the balloon. Okay. That's what we are trying to find out, the volume of the balloon. And the balloon is filled with hydrogen gas. Okay, as you can see here, the balloon was filled with hydrogen gas. The mass of hydrogen gas is given, its temperature is given in Celsius, and the pressure is given in millimeter mercury. You need to calculate the volume of the balloon. Then what we're going to do, we're going to use the ideal gas law equation, and once we are given all these numbers, all we have to do is that to convert it to the correct unit, and then we could rewrite the equation and solve it for V. Okay, that's what we will be doing. All right, then first I'm going to convert the mass of a hydrogen gas to its number of moles. Remember, hydrogen is one of those diatomic compounds. Always comes in forms of H2. Then 1 mole of hydrogen gas is 2 times 9 gram per mole. Okay, what I'm doing here, I'm converting the mass of hydrogen gas to its mole using the molecular weight of hydrogen gas. And if we do it, we get 129.9732 mole. Then we're going to take care of the sig fig. This number is 3 sig fig. This number is 3, 4, 5. Between 3 and 5, we choose 3. That's how I'm going to do my dotted line. And then I'm going to write my rounded number, which is 129.9. Then it will be 130. Okay, put the decimal to make it 3 sig fig. If you don't put the decimal, it will be 2 sig fig. That's why I'm putting the decimal to make it 3 sig fig. Or you could write it as 1.30 times 10 to the power of 2. It doesn't matter. Okay? It doesn't matter how you write it. As long as it's 3 sig fig, you're all good to go. Now, this is the number of moles. That one I have. Next thing, I'm going to convert the temperature from Celsius to Kelvin. I've already talked about unit conversion for temperature on chapter 2. Then this is the equation, okay, which will be 2783.15 plus, okay, then let me write down the equation, just a reminder. The temperature in Kelvin is equal to the temperature in Celsius plus 2783.15. Okay, therefore the temperature in Kelvin is going to be the temperature in Celsius plus 2783.15. Okay, then if you do the math, you get 296.15 Kelvin. Now let's do the decimal. Let's do the sig fig. Okay, we are adding, we go by decimal. Okay, and we always look at the given number. We don't look at the conversion. Okay, you don't look at the decimal for this. We don't care. That's the given number. Always look at, that's the conversion. Always look at the given number. That given number, since we are adding, we go by decimal rule, it's 1 decimal. That's why your answer has to be 1 decimal. Okay, and the rounded number will be 296.2 Kelvin. All right, okay, I have the number of moles, I have the temperature. Now I need to calculate or convert the unit for pressure from millimeter mercury to atmosphere. And based on the conversion value, 1 atmosphere is 760 millimeter mercury. Again, these numbers will be always given to you. You don't need to memorize it. Okay. Now, I set up my equations so that if we cancel out the millimeter mercuries, and I will end up with atmosphere. Then what we have to do is to divide 750.0 by 760, and we get 0.9868 42. Once you have your unrounded value, then you're going to take care of the sig fig. Okay, the sig fig, always look at the given number. This number is 4 sig fig. That's why your answer has to be 1, 2, 3, 4 sig fig. Okay. Then 760 is for conversion value. It's insignificant. And therefore, our rounded number is going to be 0.9868 atmosphere. Okay. Now, let's set up our gas law equation. PV equal to nRT. Okay, this is the gas law equation. Now we're going to rewrite it. Since we are solving for volume, we're going to rewrite it in terms of volume, which is going to be nRT divided by P. Okay, now I'm going to plug in all the numbers that I calculated above. Volume is equal to N is the number of moles, 130. R is the ideal gas law constant. (08206) and T is the temperature in Kelvin, divided by P, which is the pressure in atmosphere. 9868 atmosphere. Okay, let's write the unit for this one, which is in 0.2 Kelvin. Okay, when you plug in all the numbers and do the calculation, you will get the volume as 3,303.6305 liter. Okay, that's the volume. Now let's take care of the sigfig. All right, the number of moles here, 130 point, is 3 sigfig. Okay, gas law constant is a constant, we don't look for it. Temperature is 4 sigfig, and pressure is also 4 sigfig. Okay, then between 3 and 4, we choose 3, which is the smallest. That's where my dotted line gonna go. Then when I got my dotted line, I write down the rounded number, which is 3.20 times 10 to the power of 3 liter. Okay, this will be the volume of the gas. Okay, that's how it was, or the volume of the balloon. It's the same as the volume of the gas because the balloon is filled with air. Okay, then these are very simple calculations, but the only thing that you have to pay attention is that to make sure the unit for the number of moles is in mole. Let me see why it's not working. The unit for the number of moles is in mole, the unit for temperature is in Kelvin, and the unit for pressure is in atmosphere. Okay, it's really important. Also, if you are using volume, you want to make sure the unit for volume is in liter, or when you calculate it, the volume unit will be liter. Then as you could see here, I converted all those unit values that were not what I needed. Okay, all right, now let's do a quick review of the gas law. Okay, then we talked about Boyle's law. Boyle's law, the volume and the pressure was our variables. The number of moles and the temperature was constant. Okay, and what Boyle's law discovered was that the volume of the gas was indirectly proportional to temperature. Okay, which means the volume of the gas is indirectly proportional to pressure. Okay, Charles' law. Charles' law, the variables were the volume and temperature, constants were the number of mole and pressure, and what he discovered was that the volume of the gas is directly proportional to temperature. Okay, which means when he increased the temperature, the volume of the gas increased. And then Avogadro's law. In Avogadro's law, the volume and the number of moles of the gas were the variables. Temperature and pressure were the constant quantities. And what he discovered was that, let's write it down, was that the volume of the gas is directly proportional to the number of moles of gas particles. And then when we combine these three laws, we get the ideal gas law, which is PV equal to nRT. Okay, and R is the ideal gas law constant. Ideal gas law constant. Okay, all right. Now let's continue with this chapter and talk about partial pressures in mixture of gases. Then based on the kinetic molecular theory that we talked about earlier on in this chapter, since the gas particles are so apart from each other, they do not interact with one another. They neither repel each other or attract to each other because they're so apart, there's large space between them. That is why when we have more than one gas particles, they act independent of each other, as if no other gas particle exists, as if they are the only gas particles. Okay, and therefore the pressure exerted by those individual gas particles in a gas mixture is called partial pressure, okay, of that component. Then if you have only one gas particle, the pressure is the same. But when you have a mixture of gases, the pressure that's exerted by each of these gas particles, we call that pressure partial pressure. Now let's talk about Dalton's law of partial pressure. By Dalton's law of partial pressure, the total pressure is equal to sum of, then by Dalton's law of partial pressure, the total pressure in your gas container is equal to the sum of partial pressure of individual gas particles. For example, if we have this container and we have a hydrogen gas, oxygen gas, and nitrogen gas, the total pressure inside this container, it will be equal to the sum of partial pressure of hydrogen gas plus oxygen gas plus nitrogen gas. Okay, that's what it means by Dalton's law of partial pressure. Okay, and when you are adding up all these different pressure values, which we call them partial pressure, you have to make sure they all have the same unit. If they do not have the same unit, you cannot add them up. You have to convert them so that they are all the same unit, and then you could add them all up. Okay, let's do this example regarding Dalton's law of partial pressure. Okay, all right, then based on this example, we have potassium chlorate, okay, and it decomposes into, as you could see on this balanced chemical equation, potassium chlorate decomposes into potassium chloride and oxygen gas. Okay, then the question asks us how many moles of oxygen gas is collected. Okay, but we are told a whole bunch of values so that we are able to do the calculation. Okay, all right. We do know the volume of the gas. It's a milliliter, which we have to convert it to liter. We know the temperature in Celsius, which we have to convert it to Kelvin. And we know the total pressure is in torr. Okay. Then if you look at inside this inverted beaker, other than oxygen gas, we also have gaseous water. Okay. Then other than, let me draw a little picture of it. Okay. Then inside this gas container is this inverted beaker. Okay. And inside of it, let me do it this another good of a artist. All right, I don't do the rest. Then inside this inverted beaker, what we have oxygen gas and we have gaseous water. Okay, H2O, gaseous water. Okay, erase it and write it properly so that you can see it. H2O. All right, that's why what we want to find out in order to be able to do the calculation and find the number of moles, what we need to find out is the pressure of oxygen gas. Okay, but inside the container, other than oxygen gas, we have gaseous water. Then what we have to do here is that we're going to use the Dalton law of partial pressure. Okay, we have the total pressure. We are given the pressure of gaseous water, and we could easily calculate the pressure of oxygen gas. Okay, and once we have all these, we could easily calculate the moles of oxygen gas collected using ideal gas law equation. Then let's start with all these calculations. All right. Then the first thing that I'm going to do the pressure. Okay. Then inside that inverted beaker, I have oxygen gas and gaseous water. That's why the total pressure is equal to the partial pressure of oxygen gas plus partial pressure of gaseous water. Okay. Then the total pressure is given to us. 700. Oh, actually, let me rewrite this in terms of partial pressure of oxygen gas, which is equal to P total minus partial pressure of gaseous water. Then the partial pressure, the total pressure is given to us. It's 751.0 torr. Also, the partial pressure of gaseous water is given to us at this temperature. Since we are working at this temperature, there is a table with different values for partial pressure of water at different temperature. I've already given this to you. Okay, if it wasn't given to you, you could go to any literature and find the partial pressure of water at different temperature. Okay, then at this temperature, that's the value for partial pressure of water. Okay. Now, let's convert this. But before I do the conversion, as you could see here, the unit for vapor pressure of water is in millimeter mercury. We are subtracting numbers in torr. Then what we have to do is to convert 21. Let me choose a different color. 21 millimeter mercury to torr. Okay. And as you could see here, 1 torr is equal to 1 millimeter mercury. 1 torr is equal to 1 millimeter mercury. Okay, this conversion value will be given to you if you need it. Therefore, 21.07 millimeter mercury is also equal to 21.07 torr. Right. Now, once you have that number, you want to proceed with your calculation. And when you subtract these numbers, you will get 729.9 torr. Okay. Now, look here. We are subtracting. We go by decimal rule. This number is 1 decimal place. The second number is 2 decimal place. That's why your number will be 1 decimal place. Okay, we go by the lowest. Then this number is the partial pressure of oxygen gas. Partial pressure of oxygen gas. But remember, whenever we are using the gas law equation, we have to convert it to atmosphere. Now what I'm going to do here, I'm going to convert 729.9 torr to atmosphere. Okay. Then I'm going to go from torr to millimeter mercury to atmosphere. Then I'm going to set up my first equation. My first equation so that I could easily cancel out torr. And I'm going to set up the second equation so that I will cancel out millimeter mercury and I will end up with atmosphere. Okay. Then as you can see here, you can easily cancel out torr and I could easily cancel out millimeter mercury and I will end up with atmosphere, which is 0.960 0.394736 atmosphere. Now you have to take care of the sig fig. That's 4 sig fig. The rest are conversion values, we don't care. That's why your answer has to be 4 sig fig. Okay? And then you're gonna write down the rounded number. 0.9604 atmosphere. Okay? This is the partial pressure of oxygen gas. Okay? In atmosphere. Now, in order to find the number of moles, we need other values too. Okay? The next, what I'm going to do, I am going to convert the temperature. Okay? The temperature is given is 23 degrees Celsius. I'm going to convert 23 degrees Celsius. I'll just write it 23 to Kelvin. Okay, just gonna add it up, and I get 296.15. And again, for the sake of sig fig, we are adding. We go by decimal rule. We only look at the given number, which is 1 decimal. That's why your answer has to be 1 decimal. Okay. This is the temperature in Kelvin. Then we have the pressure, we have the temperature. Next, we're going to calculate the volume. The volume is given. Okay. The volume is given is 81.2, but it's in milliliter. I have to convert it to liter. Okay, that's what I'm going to do. And here, I'm going to convert the volume from milliliter to liter. Okay, then 281.2 milliliter. Okay, then 1 liter is 1000 milliliter, right? Okay, then it's going to be 81.2 times 10 to the power of -3 liter. And as you can see, I could easily cancel out milliliter and I end up with liter. Okay, then this is the volume. Oops. This is the volume in liter. Then I have the volume in liter here, and in the previous slide I calculate the pressure, the partial pressure of oxygen in the atmosphere. I calculate the temperature in Kelvin. Now I could easily calculate the number of moles, because if you look at the gas law, ideal gas law equation, again PV is equal to nRT. You're gonna solve it for the number of moles, which is PV divided by RT. Okay, then the number of moles is equal to, okay, pressure. The pressure, as you can see, oops, the pressure, sorry, I kind of messed it up. Okay, the pressure, it was calculated to be 0.9604 atmosphere. 0.9604 atmosphere. The volume is calculated as 81.2 times 10 to the power of -3 liter. And the gas law constant is 0.08206. And the temperature in the previous slide was calculated to be 296.2 liter. Oh, sorry, Kelvin. Then if you do the math, you will get the number of moles to be 3.20552 times 10 to the power of negative 3 moles of oxygen gas. Okay, now we're going to take care of the sig fig. Right, this number is 4 sig fig. The volume is 3 sig fig. The temperature is 4 sig fig. And gas law constant is a constant. We don't look at it. Then between 4 and 3 and 4, we go by least, which is 3. And therefore, your net rounded number is equal to 3.21 times 10 to the power of negative 3 moles of oxygen gas. And this is the number of moles of oxygen gas. Sorry, let me fix that one. This is the number of moles of oxygen gas being collected. Okay, then one more time, let's go over it. Here, that's a setup for decomposition of potassium chlorate, which it decomposes into potassium chloride and oxygen gas. Then inside the inverted beaker, we have gaseous water and oxygen gas. The vapor pressure of water at this temperature is 21.07 millimeter mercury. This is out of a literature. Even if it was not given to you, you could always find out when you go to any literature. Then the first thing that I want to do was to find the number of, the partial pressure of oxygen gas. The total pressure is given to me. The vapor pressure of water is also given to us. I could easily calculate the partial pressure of oxygen gas using the Dalton's law of partial pressure, which I subtracted the total pressure from partial pressure of vapor, or from vapor pressure of water. Okay. Now, because we are using the gas law equation, we need the partial pressure of oxygen gas to be in atmosphere, the unit for it, and it's in torr. Then what I did was that to convert the unit from torr to atmosphere, okay, which this is, I calculated to be that number. Temperature is given, but it's in Celsius. Again, it has to be in Kelvin. And I converted it from Celsius to Kelvin, and I added to 273.15. This equation will be always given to you, okay? Not the 23. Instead of 23, we put temperature in Celsius, okay? And when we are adding, we go by decimal rule, 1 decimal. We always look at the given number. That's why the answer is 1 decimal. This is the temperature in Kelvin. And then I calculated the volume, converted the unit. It was given. I just converted the unit from milliliter to liter. Once I have all these three numbers that I need, I solve the gas law equation in terms of the number of moles, and I calculated it, the number of moles of oxygen gas that was collected, okay, which is this number. Now this question has a second part, and the part B asks us how many moles of potassium chlorate were decomposed. Then from part A below, the moles of oxygen gas was calculated, okay. Then based on this balanced chemical equation, I'm going to convert the moles of oxygen gas to the moles of potassium chlorate. Okay, that's all we will be doing. Then 3.21 negative 10 to the power of negative 3 moles of oxygen gas. I'm going to set up so that the moles of oxygen gas are going to get canceled out, and I end up with moles of potassium chlorate. Okay, which will be equal to 2.14 times 10 to the power of negative 3 moles of potassium chlorate. Okay, and as you can see here, this number is 3 sig fig. That number will be 3 sig fig. Always look at the given number. Okay, so how did I get this number? I calculated it in the previous slide. Then I use that number. I use this balanced chemical equation, and I converted the moles of oxygen gas to the moles of potassium chlorate solid. That's all I did. Now let's continue with our definition for partial pressure and use this equation right here and convert partial pressure of each component to find out the fractional composition of each component. Okay, then we're going to use this formula to calculate the fractional composition of each component using the total pressure and the partial pressure. Or sometimes the fractional composition is given to us, the total pressure is given to us, and we could easily calculate the partial pressure of each component. Okay, now let's do a problem, and you will know what I mean by this type of conversions. All right, then if you look at this example, we have a gas mixture. Then we have this container, and this container contains 78% nitrogen gas and 22.0% oxygen gas. Again, these are diatomic compounds. Okay, we call it N2, O2. Okay, now we do know the total pressure. Okay, we also know the fractional composition of each component. Okay, and what we want to find out is the partial pressure. Then going back to my previous equation, then as you could, based on the example, this number is given to us, that number is given to us. All we need to do is to calculate this number. Okay, that's what we're trying to do in this problem. Okay, then the partial pressure of nitrogen gas, okay, based on the equation in the previous page, is equal to the fractional composition of nitrogen gas. Okay, since this number is in percentile, you have to convert it to actual number. Okay, then to make a number percentile, you multiply by 100. To remove that percentile, you divide it by 100. And I'm going to say 78.0 divided by 100. Okay, just to remove that number and the percentile to make it actual number, times the total pressure, and the total pressure is 1.112 atmosphere, okay, which will be equal to 0.8736 atmosphere. Okay, now for sig fig purposes, this number is 3 sig fig, 100 is insignificant, and that number is 3 sig fig. That's why our answer is going to be 3 sig fig. Then this number will be the partial pressure of nitrogen gas. And we're going to do the exact same thing for oxygen gas. Okay? Then partial pressure of oxygen gas is equal to fractional composition of oxygen gas. It's in percentile. I'm going to remove the percentile by dividing it by 100 times the total pressure, which is 1.12 atmosphere. Okay. If you do the multiplication, you get now number as 0.2464 atmosphere. Okay, and again we do sig fig, 3 sig fig, 100 is insignificant, 1.12 is also 3 sig fig, and therefore your answer has to be 3 sig fig. And therefore the answer is going to be 0.246 atmosphere. And this will be the partial pressure of oxygen gas. Now, let's talk about the use of gases in chemical reactions and stoichiometry. In the potassium chloride experiment and the calculation that I did, I'll show you guys how I could use the gases and gas equations and the stoichiometry to convert between different variables. Okay, then this is the ideal gas law equation. As you can see, it is rewritten so that we could solve it in terms of number of moles. Okay, Then once you find the number of moles of one of the gas particles, okay, knowing its pressure in atmosphere, volume in liter, temperature in Kelvin, you could use that number of moles and you could use your balanced chemical equation and convert that number of moles to the other quantities in that chemical reaction. Okay, then you could use that number of moles and you could convert it in order to calculate other quantities in your reaction. Okay. Now let's do a little problem or example. In this example, as you could see in this equation, okay, this is the equation for synthesis of ammonium sulfate, okay, which is a reaction between ammonium and sulfuric acid. What you want to calculate, you want to calculate the volume of ammonia that was used. Okay. The temperature is given, the pressure is given. The volume and the concentration of sulfuric acid is also given. Then you're going to use the molarity and the volume of sulfuric acid, find the moles of sulfuric acid. Once we find the moles of sulfuric acid, we convert the moles of sulfuric acid to the moles of ammonia based on this balanced chemical equation. And then once you know the moles of ammonia, you're going to use the ideal gas law equation and you're going to plug in these two parameters and it will calculate the volume of ammonia. Okay, now let's do it. Let's start on it. Okay, then the first thing that I'm going to do, I'm going to use the concentration of sulfuric acid moles per liter of sulfuric acid, and I'm going to find the moles of sulfuric acid. Okay, it's just a matter of multiplication. Then if you do that, the moles of sulfuric acid is going to be equal to 541.8 mole. Now we have to do the sig fig. 3 sig fig. The volume is 3 sig fig. Your answer has to be 3 sig fig. Okay, and this will be the moles of sulfuric acid. Now, I'm going to convert the moles of sulfuric acid to the moles of ammonia based on this balanced chemical equation. Okay, then 500, let's use 542 moles of sulfuric acid times, you're going to set it up so that the moles of sulfuric acid cancel out, you end up with moles of ammonia. Okay, then based on this balanced chemical equation, 2 moles of ammonia is proportional to 1 mole of sulfuric acid. Okay, and I set up my equation so that the moles of sulfuric acid will be canceled out and I will end up with moles of ammonia. Okay, then you get 1084 moles of ammonia. Okay, and again you have to take care of the sig fig. This number is 3 sig fig. That's why your answer has to be 3 sig fig. Okay, that's equal to 1.08 times 10 to the power of 3 moles of ammonia. I did this in 2 different steps. You're more than welcome doing it in 1 step. Okay, you could directly convert the moles of, in 1 step, the moles of sulfuric acid to the moles of ammonia. Okay, you do it in 1 step as I have done it in the past, but I did it in just 2 steps. It doesn't matter. Okay, now that you know the moles of ammonia, what I'm going to use, I'm going to convert the temperature from Celsius to Kelvin. And 42 plus 273.15 is the conversion value, will be equal to 315.15 Kelvin. Then we are adding, we go by decimal rule. This number is one decimal. 273.15 is a given number. It's the conversion value. We don't care about it. That's why our answer has to be one decimal. Then the temperature is going to be 315.2 Kelvin. This is the temperature. Okay. And the volume is given to me right here. Then I'm going to rewrite the gas law equation. And I'm going to solve it in terms of the number of moles. In terms of volume. Because that's what we're going to calculate. It's going to be P, which is going to be nRT, okay, over P. Now what I'm going to do here, I'm going to plug in the values. I have the number of moles. I calculate to be 1.08 times 10 to the power of 3 mole. I have the ideal gas law constant. I know it is 0.08206. And I know the temperature. I just calculated it in Kelvin or converted it to Kelvin. It was given in Celsius. And I divide it by pressure. Okay. And this pressure is given to us also, which is 15.6. Okay, it's given, it's right here. Right. Then when you plug in these numbers in your calculator and calculate the numbers, you get 1.791548 times 10 to the power of 3 liter. Now the next thing that we got to do is to take care of the sig fig. 1.08 is 3 sig fig. We don't care about the gas law constant. Temperature is 4 sig fig. And pressure is also 3 sig fig. Then between 3 and 4, we choose 3. Okay. Therefore, the answer is going to be 1.79 times 10 to the power of 3 liter. This is the volume of ammonia needed for the reaction to proceed. Okay. Now, let's continue and let's talk about molar volume and standard temperature pressure. Okay. The molar volume, by definition, is the volume occupied by 1 mole of gas. The temperature has to be 273.15 Kelvin or 0 degrees Celsius. The pressure has to be 1 atmosphere. And the volume has to be 22.4 liter. Okay. When you meet these conditions, okay, that's what it means by a standard temperature pressure. Which means at standard temperature pressure, the number of moles is 1 mole. That's the number of moles. The temperature is either 0 Celsius or 273.15 Kelvin. The pressure has to be 1 atmosphere and the volume has to be 22.4 liter. Then once you meet these conditions, okay, you will have standard temperature and pressure. Sometimes you have heard some measurements being done at standard temperature pressure. That's what it means by standard temperature and pressure. Now let's talk about molar volume. Molar volume is the volume occupied by 1 mole of gas under a standard temperature pressure. That's what it means. Okay? Then the molar volume is the volume occupied by 1 mole of the gas under standard temperature and pressure. And this is the ratio that we use as a conversion factor in standard temperature pressure conditions, okay? Which you could convert the moles to molar volume, okay? Then we're going to use this ratio, which you need to know it, to be able to convert between the number of moles or the volume of the gas in standard temperature pressure conditions. Okay. Now let's do this problem. Okay. There is a sample of oxygen gas with a volume of 2.50 at standard temperature pressure. You want to calculate the mass of the gas, the mass of oxygen gas. Okay. Then you have the volume. Okay. Then you're going to use this equation right here. Okay. And you're going to convert the volume to the moles of oxygen gas. Once you know the moles of oxygen gas, using its molar mass or molecular weight, you will find the mass. Okay. Then I'm going to use this conversion to convert the volume to the number of moles. Okay. Then 2.50. Right. I'm going to set up the conversion so that I could cancel out the liter and I end up with moles. Okay. That's my conversion. And you see that STP, as soon as you see that STP right here, that means it's standard temperature, pressure, and you can use that molar conversions, molar volume conversion. If you don't have that STP, you cannot use it. It has to mention that it's at standard temperature, pressure. Okay. Then I set up this equation so that I could cancel out the liter, and I end up with number of moles. Okay. It should be 0.111607 moles of oxygen. Next, we have to take care of the sig fig. This number is 3 sig fig. 22.4 is a conversion value. We don't take it into account. It's not significant. Then your answer has to be 3 sig fig. That's where the dotted line gonna go, which is equal to the rounded number to be 0.112 moles of oxygen. Okay, this is the moles of oxygen gas, but the question asks us for mass. Then I'm going to use this number and I'm going to use the molecular weight of oxygen gas, and I'm going to convert the moles of oxygen gas to its mass. Okay, it's 2 times 15.9994 grams of oxygen. Okay. Then if you do the calculation, you will get 3.58387 grams of oxygen. Again, let's take care of the sig fig. This number is 3 sig fig. And the molecular weight is 1, 2, 3, 4, 5, 6. Then between 3 and 6, we go by 3. And the answer will be 3.58 grams of oxygen gas. Okay. Then let's go over this one more time. Then the volume is given at standard temperature pressure. As soon as you see that standard temperature pressure, you could use this conversion factor. Okay, if you did not set a standard temperature pressure or STP, you could not use it. but since it's mentioned, you can use it. Then I use this conversion factor and I converted the volume to the moles of oxygen gas. Once I have the moles of oxygen gas, I use the molar mass or the molecular weight of oxygen gas, and I set up the equation so that the moles of oxygen gas could be canceled out, and I would have ended up with mass of oxygen gas. This will be the answer. As you could see, the moles of oxygen gas, you can see it easily cancel out. This is the end of chapter 11 lecture, and thank you for listening to my lecture.